In this part of Lecture 6, we'll be talking about the entropy of mixing, when in fact there's no energy change within the system. Let's sort of set that up. Well, this is the equation we want to get here, and let's set that up by drawing a picture. All right, so suppose we have two gases, and let's make these gases argon. We'll separate two volumes here, put argon over there, and put helium over here. Argon will occupy some volume argon, and this will occupy some volume helium. And there's a partition between the chambers in this system, so it keeps all the helium over here and all the argon over here, and what we're going to do is remove that partition. This will be some temperature, say, of argon, some pressure of argon over here, some number of moles of argon over here. Same way here we have temperature helium, pressure of the helium, and the number of moles of helium. Let's assume that the temperature of argon is equal to the temperature of helium, so there's no temperature gradient. Pressure of argon is equal to the pressure of helium, so there's no pressure gradient. And of course the number of moles will be different between the two systems if the volumes are different. What we're going to do is to remove this partition, just take it away magically, and what we're going to end up with is argon plus helium mixed, and the temperature will be the same as the temperature before removing the partition, as will the pressure. Now there's no gradient in temperature here, so there'll be no transfer of heat between these two chambers. There's no pressure gradient, so there'll be no transfer of volume between them. The volume, is different here, but when we remove it, we'll have a total volume. So there's really no work being done, nothing going on here. But what we find is that, in fact, the argon diffuses into the helium diffuses in the argon, and at the end of the process, when it reaches equilibrium, the argon and helium are mixed. There's nothing driving this. According to the first law of thermodynamics, there's no gradients in temperature or pressure, nothing going on here, but nonetheless this process happens spontaneously and only in one direction. You never see the argon in this system spontaneously collecting over on the left, and you never see the helium spontaneously collecting over on the right. This is an example why we needed the second law of thermodynamics. So to describe why this only goes one way, we're going to calculate the entropy change, and we'll find the entropy change for this process is positive, so entropy will increase, and the second law of thermodynamics predicts this will be a spontaneous process. Alright, so how do we calculate the entropy change? There's no work or heat being done on or by the system or anything. Well, there is a volume change. Here argon is constrained to this volume. When you remove the partition, argon now has the entire volume to move around. And the same way with helium. To calculate the entropy change when volume changes, that's just nR times the natural log of the final volume divided by the initial volume. Let's do that calculation for argon for the system in the previous slide. So delta S is the number of moles of argon times R times the natural log. Let's see, the final volume is the total volume, the sum of the two volumes before we remove that partition. So this will be the total volume, and the initial volume, argon was constrained to move in this volume here. So that'll be the volume of the argon. And we can write a similar equation for the entropy change for helium. That'll be the number of moles of helium times R times the natural log of the total volume divided by the volume that helium initially occupied. Entropy is a state function, so the entropy change going from here to here is the entropy change of the argon plus the entropy change of the helium. So entropy change is the entropy change of argon plus the entropy change of helium, and just equal the number of moles of argon times R times the natural log of the total volume divided by the volume of argon plus the number of moles of helium times R times the natural log of the total volume over the volume of helium. Let's pull R out. R is a constant. Pull that out of the sum. This will be R, number of moles of argon times the natural log of the total volume divided by the volume occupied by argon plus the number of moles of helium times r times the natural log. Ooh, we pulled that r out. Ooh, forgot about that. Sorry. I love that eraser function. Times the natural log of volume total divided by volume helium. It'd be nice if life had an eraser function. That's what this is, so we just got that equation there. Let's introduce this term here. This is called the mole fraction of A. That will be defined as the number of moles of A divided by the total moles. This is the Greek letter chi, and this will be called the mole fraction. That's a unit, a concentration unit that was introduced in introductory chemistry. If that's the case, then, let's go down here, this is a process that has constant temperature and pressure. This implies from, what's the name, Avogadro's law, that the volume occupied by, say, argon divided by the total volume is equal to the number of moles of argon over the total number of moles. And we're assuming now an ideal gas. From Avogadro's law, that's what we get. Let's rewrite one of these expressions, say delta S for argon, we said was N, number of moles of argon, times R, times the natural log of the total volume, or the volume occupied by argon. That's equal to the number of moles of argon times R times the natural log. Look, volume of argon over volume total. This will be defined as we said in the earlier, the mole fraction of argon. So this would be 1 over the mole fraction of argon, or taking the inverse of that, that brings a minus sign over here, the number of moles of argon times R times the natural log of the mole fraction of argon. And similarly, for change in entropy of helium, that'll be just the minus the number of moles of helium times R times the natural log of the mole fraction of helium in the final mixture. So that the total will be the sum of these two, and let's pull out the R from the sum. This will be minus R times the number of moles of argon times the natural log of the mole fraction of argon plus the number of moles of helium times the natural log of the mole fraction of helium. So this is another way to write the expression of the total entropy change, and that's what this one is here. Alright, so we got a couple ways to calculate entropy changes when things just mix and there's no energy being transferred forward or backwards. And we expect that the entropy change for this will increase, so we expect that this will be a positive number. Note that mole fractions are always less equal to or less than 1, so this will give a negative value. The log of a number less than 1 is negative, and that will cancel out that negative. This term will be positive, that term will be positive, and so on. So you will get a positive entropy change.